part of a computer engineer's success within the area of computer science is his or her ability to think computationally. When discussing computer science within the realm of disciplinary literacy, we have to discuss how a computer scientist or how an engineer working with computers uses computational thinking and how they learn to think computationally. As educators, we need to help our students figure out how to think computationally and use those skills in order to develop different projects within the world of computer science. The discussion today is going to focus on a couple discussion points. The first thing I want to point out and discuss is domain-specific vocabulary. The reason I chose to put vocabulary first is because some of this vocabulary could be considered new to educators not familiar with computer science concepts. The next thing I'd like to do is discuss computer science, what it is and why it's important, and then discuss Wisconsin computer science standards. I thought it was important to look at the standards when discussing disciplinary literacy because we need to understand what we're asking students to do and what students must be proficient in order for us to teach them the skills and strategies they need to be successful. Then I'm going to talk a little bit about literacy within computer science and how we can teach students to become literate and proficient within these strategies. I'm going to focus on one strategy to build literacy skills and skills essentially in computational thinking. And then I want to talk just a little bit about the future of computer science within schools. The first vocabulary word I wanted to focus on, all of these words are presented in the Wisconsin Computer Science Standards, and I'm focusing on one standard band out of several, which is algorithms and programming. The reason I chose this band is because the project I will be showing at the end of this presentation has to do with algorithms and programming. An algorithm essentially is a process or set of rules that a computational system must follow when calculating or solving problems. An example of algorithms that you and I might use each day are cooking recipes or construction of IKEA furniture. There is a set sequence of events that we must follow within parameters that if we don't, that our end product will not come out the way we planned it to. The next one is computation, which is how these problems in efficiency are solved through the use of computation. The processes are often represented mathematically, but not necessarily, especially within computer science. Computational systems are devices that are able to make simple or complex computations. When we think about a computational system, we think about a computer. However, people seldom realize that your brain is also a computational system. If we think back to the algorithms that I talked about in terms of cooking recipes and constructions of IKEA furniture, our brains are following an algorithm in order to complete that task. Decision making is also use of algorithms, and that we have to follow our own way of weighing different outcomes of our decision and essentially and ultimately choosing the best one. The next one is computational thinking. When students think computationally, they have to start with a complex problem. Complex problems and simple problems, what we might think is a simple problem could be more of a complex problem. And I'm going to show you an example of that later in this presentation when our problem becomes breakfast. Next, we need to understand what that problem is. We need to think about all the different ways that we could possibly solve that problem and what we have to do in order to get there. Our last step then is to develop possible solutions in a way a computer, human, or both can understand. There are 5 parts to computational thinking. In my example today, I'm going to talk about decomposition, which is breaking something into smaller parts, pattern recognition, or looking at similarities and trends. In this example, it's going to be within code, abstraction, which is finding what is important in the problem and what is unimportant. We don't want to focus on those unnecessary things. We want to only focus on solving what is important. Developing an algorithm or step-by-step instructions, which we discussed before, and my first personal favorite part within coding, which is debugging, and that's fixing problems within your algorithm so that the computer can understand it. Computer science is not just computers. There's a lot that goes in behind a computer, and when thinking about computers, it's basically the scientific and engineering approach to computation. But we also need to talk about the applications and the impact of the products that we create through the use of computer science content. It studies the feasibility, structure, expression, and mechanization of the methodical procedures, which are essentially the algorithms um, that underline the acquisition, representation, processing, storage, communication of, and access to information. At the heart of computer science is information. Everything that our computational devices do work with information. So we need to figure out how to get that information. How are we going to show that information in a way that a computer or a human is going to understand? How can we help that computer or help that human process that information? Our brains and our hard drives store that information. We need to be able to communicate that information to others. And in order for us to communicate it, we must be able to access it. Both computers and humans do all of these functions. Now, this specific explanation of computer science I found it within the Idaho K-12 content computer science standards. The Wisconsin computer science standards were written based off of Idaho and a few other states' computer science standards, which leads me to 4 standards that I chose to focus on for this specific discussion of disciplinary literacy. The reason I chose these is because there are applications within these standards to other content areas besides computer science. The first one is decomposing a computational problem into different parts and then creating solutions for one or more parts of that problem. Students do this in math, they do this in science, and they also do this in language arts. So showing them other ways through computers how we can solve those same problems in those other content areas will help students understand how to better process that information. The next one is producing their own artifacts, but thinking about what the needs and wants of the community are. I chose this specific standard because a lot of people view computer science as just a man sitting in a room with code scrolling across his screen and him feverishly typing, and that's not what it is. Computer science is developed, products are developed within teams, and humans and human advancement are at the heart of each program or application that is developed by programmers. And it's important for our students to understand that and to figure out how we can solve problems within our own communities through the use of computer science. The next one is the interpreting the flow and execution of algorithms and predict their outcomes. This one I chose because this is so similar to what students do within their language arts classrooms. When they're reading and annotating a text, they need to figure out why and how that text is structured. And even in literature, why an author chose to use the words or use the phrases that they use. What are they what message are they trying to get across? Students have to do this with the code as well. And when they look at algorithms, they need to think about why a programmer would have written or used the algorithm that they used. When we interpret the flow of algorithms, students can either use natural language, which is essentially what I'm using and what we use in our annotation when we just write normal English, standard English. Flow and control diagrams kind of break it down into easier chunks that students can understand. I'm going to show an example of this later. Comments within code are really helpful. Students, when writing code or when looking at code, can actually put a comment within the code itself that tells either the student themselves or somebody else who's looking at the code what that actual block of code does, and then pseudocode, which is just simplified programming language. The last one, and one of the most important ones to me, is soliciting and integrating peer feedback as appropriate to develop and refine a problem. A lot of what computer science is communication. So it's important to teach students how to communicate about their work and their products, but also how to get feedback from others, because sometimes these problems within computer science can be so complex, and often after staring at a block of code for a long time, students can get frustrated. So if they talk about their problems with other students, they can think about their process, but that other student can then provide feedback to the student who's having an issue. After we've talked about the standards, I think it's important to talk about literacy skills in computer science. The New York Board of Education has define technology literacy as the innovation, change, or modification of the natural environment in order to satisfy perceived human wants and needs. I kind of alluded to that before, but what I think is most important is what we're asking students to be able to do. What do we want them to be proficient in? So I've kind of broken down, decomposed the standards into 5 really main functions. The first one is inquiry. The students need to figure out what a problem is and what are the different steps that we can take to solve that problem. When looking at existing code or their own code, they have to interpret it. What does the data mean? What does the code do, and why does the code work that way? It's important to do this interpretation step before we ask students to create their own code so that they can really analyze pre-existing things and understand how it works. In order to interpret it, we use decomposition, which is breaking up existing code into different functions and discussing what those functions do. After students have broken up their code, we want them to rearrange them. And going back to that computational thinking, we're looking at patterns. So they're using familiar groupings of code and trying to manipulate them to perform new functions within different situations, which will then lead our students to create their own set of their own lines of code that will solve a problem, basically using what they learned from that decomposition and that rearrangement of pre-existing code. Computer science is an interdisciplinary approach, and it should be taught this way within our schools. I think a lot of us think of computer science as a separate content area. However, computer science and education is built around the intersection of computer science and other content areas. Using concepts from computer science, students can work to create solutions to solve problems across disciplines. Computer science is creatively driven, as there's no limit to the possibilities of what students can create using computer science principles, making it one of the most versatile educational disciplines. There's really great information on this and ways to integrate computer science into your own classes. Code.org is a fantastic resource for teachers. It discusses how code can be used within the science or the math class, which we'll see soon, but also the language arts class. There's different ways to create animations using code that students can use to narrate their own stories, or all sorts of pre-existing stories in which they have to do plot diagrams and things like that. Project Guts is a really great resource that's a little less user-friendly than code.org is, but there is so much richness within the science and the mathematics content areas that really help students understand and comprehend that content area information in order for them to become proficient. Students really want to use technology, and so through the use of computer science, we can give them an outlet to understand and to learn these different concepts in a way that they enjoy. One of the strategies is to help students think computationally is the decomposition of computational problems. I want to show you a flow diagram of a computational problem, but before I go into that, I want to just make an easy visual for us to kind of show how a seemingly simple problem can actually be more complex than it is, and why we would have to plot out this problem with a flow diagram. So essentially, students take that problem, think of the possible outcomes, and create instructions of how to complete the task outlined to solve the problem. So here we have making breakfast. We skipped part of the planning process where we figured out what breakfast we wanted to make. And we made that decision that we're going to make toast and we're going to make tea. Now, these 2 separate breakfast items, we need to figure out how those things are made in order for us to have that final product of breakfast. So we would make toast, and we would go through the step-by-step instructions of how to make that toast. The same goes to make tea. Now, this is a simple problem and a simple line of code. We can make this more difficult for students and do a similar flow diagram if there were conditions. For example, if the patron wanted something sweet, then we can make them toast with jelly. So if want sweet, then, and then we would have the directions or the instructions of how to make that toast. Or we could have or the patron wants something savory, and there would be separate flow charts for each decision that our algorithm would have to make. Now, I wanted to show an example of this within the content area, and we're going to look at science and ecosystems. So if students are studying ecosystems, we could use Project Guts. There is a project in there that helps students create their own ecosystem. Now, I'm taking one piece of this project. This is a very big project with all sorts of moving parts and different ways we could use the flowchart. But when introducing the code to the students, instead of asking them to create their own code, we want them to look at a pre-existing code to see how the functions work and how they could possibly build their own code. So here we have just a small snippet of the code that is included in this program, where the computer decides whether or not a rabbit is reproduced within their ecosystem. So looking at the image on the left, it's a little bit overwhelming. Actually, it's very overwhelming. And so asking students to tell you what this means just by looking at it, it's too much to ask students. So on the right hand side here, I have an example of how a flow diagram could be used to show for students to kind of talk about and work through what this code means. So the procedure is rabbit reproduction, and we have there are two things this code does within the world. You can see those in brackets. So we have what the mom rabbit does, and then if the mom rabbit meets those specific conditionals, then it goes down to the baby rabbit code. So looking at the mom code, if the rabbit has eaten enough grass to have more than 6 energy, and those are values that have already been set within the code, then the rabbit is going to lose 3 energy, because we know that reproduction costs us energy, costs any living thing energy. So after those 3 energy have been lost, a new baby rabbit is created. Once that baby rabbit is created, we need to know what happens to that baby rabbit. So it begins with random integer of 0 to 2 energy, which then leads to the placement of baby rabbit random in the world. There is a visual piece to this, and so a baby rabbit will pop up on the screen. Now, there will have been prior discussions of what code is at this point in the students' project, and they will have some familiarization of how to use, it's called Star Logo Nova. So a lot of these words will make more sense to a student that's looking at this piece of code, and they will be able to break it down. On the left, there's a little blurb about, and we're going to that, we've decomposed the code. Now we're looking at rearranging and possibly creation. So the student noticed that, I need to have the rabbits, I need to have my grass, and I need to have and it's not mentioned here, but a predator. And so the student noticed that they can use a variation of this sequence of code for all sprites. Sprites are basically characters in the ecosystem. So this same type of code could be used, probably changed, when talking about the predator, because predators are bigger. They're going to need more. They're going to need more energy. They're also going to lose more energy. Rabbits are worth more in energy than grass is, but the grass will not have a code like this because there is no energy source programmed into the simulation. This really helps students talk through what the code does. They could do these same flowcharts then when drafting their code for their predator, and what values and what functions they would change based on the properties that they learned about predators within an ecosystem. Here's a decomposition of code, and then thoughts on how to rearrange and create new functions. Finally, I'd like to talk a little bit about the future of science literacy, because this is something that throughout my time as a teacher, I've gained more passion for. I really want other teachers to realize that that computer science should be used as an interdisciplinary approach to all content areas. It's not just limited to technology. Computer science is so versatile that it could work in any content area. Something I really look forward to doing soon, and it's a big step because there's really not a foundation built into this, but integrating computer science literacy and computer science ideas into biliteracy, and having this available to not just our English speaking students, which is really how things are set up right now. and making this accessible to students of all languages within our school. Um, it'd be a really interesting thing to play around with and see if it could happen. And another thing I find extremely important is utilizing this type of literacy in K through 12 curriculums. We typically think of computer science at the middle school or the high school level, but there are applications for this type of learning starting from kindergarten. Um, it's an extremely important part of our world, and we really need to start focusing on how we can help students become literate within computer science and how to enhance their learning in these areas.